Hello everyone, hope you are doing very well. So, today we are going to discuss the NCRT exercise questions from our chapter Haloalkanes and Haloarenes. So, let's begin today's topic NCRT chapter 6 Haloalkanes and Haloarenes. NCRT exercise question 6.9, 6.14, 6.18 and 6.19. So these are the specific questions we have chosen today because they are covering the major concepts from this chapter. This is a disclaimer. Let's begin with our first question, the exercise question 6.9. Question is, which compound in each of the following pairs will react faster in the SN2 reaction with hydroxyl ion? So we have given two parts of this question and each part containing a pair of the compounds. First part is CH3Br or CH3I. Second part CH3 whole thrice CCl or CH3Cl. So these are the two parts that have given, and you have to tell that in each of these pairs which compound will react faster according to the SN2 mechanism with the hydroxyl ion. So you have given some time, try to analyze this question and then we will see the correct answer. Okay, let's see. So for this question, let's understand first of all the SN2 reaction, the substitution nucleophilic biomolecular reaction. So this reaction rate in the molecules having same alkyl group. So if your alkyl halide have same alkyl group, okay, so you have different molecules but their alkyl groups are same, the R is same, then how the reaction rate will be? So if your alkyl groups are same, then the rate of the reaction will depends upon the type of living group present in the molecule. That means the halide ion that is present in that molecule. So on that halide ion, on that living group, the rate of reaction will depends upon in the SN2 reaction. Rate will be faster in the molecules which is having better living group, because as soon as the living group left from the molecule and forms a carbocation, the nucleophile can attack on the carbocation and make the bond, right? So for the SN2 reaction, if you are having same alkyl group and the rate of reaction is depending upon the type of living group, right? So if you have a better living group in the molecule, then the rate will be faster. So if the living group, that means halide ion, as I said, is having larger size, then the reaction rate will be more. Okay, why? Because if your living group is larger in the size, the bond between the carbon and the living group will be weaker and can break easily. So you will form, or the formation of carbocation will be more easily, right? And there will be availability of the bonding with the nucleophile with this carbocation. So reaction rate will be more. So order of reactivity, if you see, when you are having same alkyl group and different type of living group, the order of reactivity will be highest for alkyl iodide, then for alkyl bromide, then for alkyl chloride, and then least reactivity is for alkyl fluoride, because fluoride is having the smallest, or you can say size, right? Iodine in the halogen atoms, iodine have largest size, right? So that's why the alkyl iodide will be having the greatest reactivity, because it will be it will show the more reaction rate, because iodine here, iodide ion, is a living group which is a better living group due to its increase of size, or its larger size, due to which the carbon and the iodine bond will break easily. Now let's take the second case where you have different alkyl groups in the molecules. Now R is different. Okay, then the rate of reaction will depend upon the nature of carbon present, because if you have different alkyl group, then that also going to affect the rate of the reaction, right? So if you have different alkyl group, then what is the nature of carbon on which the nucleophile is going to attack? On that factor the rate of reaction is going to depend upon. So here, when you have different alkyl groups, steric hindrance is the major factor. Okay, so the incoming nucleophile which is going to attack on the carbon from the opposite side of carbon halogen bond, it should face lesser steric hindrance to bond with carbocation, to bond with carbon, right? So steric hindrance is the major factor in this SN2 reaction, and order of reactivity will be highest from the primary carbocation, then for secondary carbocation, and then for tertiary carbocation. Or you can also say that order of reactivity will be highest for a primary alkyl halide, because it will going to give you the primary carbocation. Then for secondary alkyl halide, and the least order of reactivity is, or you can say least reactivity is for tertiary alkyl halide, because it is going to give you a tertiary carbocation, which is going to like when the nucleophile is going to attack on the tertiary carbocation, it will face steric hindrance in the case of tertiary carbocation, right? So this is the order of reactivity when you have different alkyl groups. So the rate of reaction is depending upon overall on the nature of carbon that is present on which the nucleophile is going to bond with. Let's see the first part of this question. The pair CH3Br or CH3I, iodomethyl or bromomethyl. Here you can see that both molecules contain same alkyl group, which is methyl group, and the leaving group are different. So rate will depend upon the type of leaving group. So we have iodine and bromine as a leaving group present. So iodine have, or you can say iodine is the better leaving group if you compare with the bromine, right? So iodine is better leaving group as compared to bromine. Why is it so? Because iodine have larger size, so with increase in size halide become a better leaving group, and iodine obviously has larger size compared to the bromine, right? Because if you see in the group of halogen, group 17, you will see that when you go from top to bottom, okay, at the bottom most, or from top to bottom, the size, the atomic size increases in the halogens. So the iodine comes at the very bottom of the group, so it will have a larger size compared to the bromine, and with the increase in the size, the fact that with increase of the size, halide becomes a better leaving group. And if we have a better leaving group and same alkyl group present in the molecules, then the rate of reaction will be larger, or will be more with the molecule of better leaving group. So therefore your CH3I, okay, that means iodomethyl, will react faster than the bromomethyl in the SN2 reactions with hydroxyl ion. Hydroxyl ion here is a nucleophile. Okay, so why iodomethyl will react faster? Because it contains a better leaving group, that is iodine. Okay, now let's see the second part of this question, that is CH3 whole thrice CCl or CH3Cl. Now if you can clearly see that in these two you can say molecules, we have different alkyl groups, right? So here we have tertiary butyl group, and here we have methyl group, right? Both are different. Now we are putting a star on this carbon, because on this carbon your hydroxyl ion, your nucleophile is going to attack, or your nucleophile is going to bond with. Okay, So this first compound is tertiary butyl chloride. This is a tertiary alkyl halide because the halogen chlorine here is binding with the carbon, which is bonding with other 3 carbons. And here in the methyl chloride, the chlorine is attaching with only 1 carbon, right? So this is a primary alkyl halide. Now, for if you have different alkyl groups in your molecules, the rate of SN2 reaction will depend upon the nature of carbon that is present. Okay, because alkyl groups are different. Okay, you can say chlorine is same, but alkyl group are different. So, what is the nature of carbon on which your hydroxyl ion or on which your nucleophile is going to bond with? So, the nature of carbon will going to depend or will going to determine the rate of the SN2 reaction. So the primary carbon reacts at very fast rate, then the secondary or tertiary carbons, and tertiary carbons are least reactive. Okay, why? Because there is so much steric hindrance in the tertiary carbons. Because if you see this tertiary butyl chloride, around this carbon, star carbon, we have 3 different methyl groups are attached to it. Okay, now when hydroxyl group attack on this carbon to bond with from the opposite side of carbon chlorine bond, so it will face steric hindrance due to the presence of these large methyl groups. Comparatively to this methyl chloride, this carbon, when the hydroxyl ion will attack on this carbon to bind with it from the opposite side of carbon chlorine bond, this carbon containing only 3 hydrogen binding with it. Comparatively, the hydroxyl will face lesser steric hindrance or no steric hindrance in this case in the methyl chloride, right? Because the carbon is attaching with smaller hydrogen molecules comparatively to this tertiary carbon, which is attaching with larger methyl groups, right? So here the hydroxyl ion will face more steric hindrance. That's why we are saying that primary carbon reacts at very fast rate, then the secondary carbon, and tertiary carbons are least reactive in the SN2 reaction. So compound A is a tertiary halide, as I said, and compound B is a primary halide. So tertiary halide is more sterically hindered than the primary halide due to the presence of these 3 methyl groups, the larger groups around this carbon. That's why your methyl chloride will react faster than tertiary butyl chloride in the SN2 reaction with this hydroxyl ion as a nucleophile. Okay, let's see our next question, exercise question 6.14. The question is, write the structure of major organic product in each of the following reactions. So we have given 8 reactions. You have to write the major product which you will get in each of the reactions. The first part is your chloropropyl reacting with sodium iodide in the presence of acetone and heating. Then what will be the major product? Second, CH3 whole thrice CBr plus KOH in the presence of ethanol and heat. Then you have to tell the major product. Third is CH3CH Br CH2CH3 plus sodium hydroxide in presence of water. Then you have to tell the major product. Fourth is CH3CH2Br plus KCN in the presence of aqueous ethanol. And then you have to tell the major product. Fifth, C6H5ONA. Now this is benzene ring. Okay, sodium. You can say so ONA is connecting with the benzene ring plus C2H5Cl. Then what will be the major organic product you will get, that you have to tell. Sixth part, CH3CH2CH2OH. That is this is an alcohol plus SOCl2. What will be the major product? Seventh part, CH3CH2CH double bond CH2 plus HBr in the presence of peroxide, and the eighth reaction is CH3CH double bond C CH3 whole twice plus HBr. Then you have to tell the major organic product. Okay, so for each of these 8 reactions, you have to tell the major product that we are obtaining in these each reaction. So you have given some time, try to solve this question, and then we will see the correct answer. Okay, let's see. So let's see for the first reaction, and this is the alkyl halide. So reaction of alkyl chloride with sodium iodide in presence of acetone will yield alkyl iodide. So this reaction is for the preparation of iodine substituted haloalkanes. Okay, so your this reaction of alkyl halide with the sodium iodide is also known as Finkelstein reaction or halogen exchange method. So this reaction will proceed via halogen exchange method. Why we are saying halogen exchange? So you can clearly see one chloropropane when reacts with sodium iodide. These two halogens, the chlorine and iodine, replaces each other, exchange each other places. So this reaction happens in presence of acetone and heat, and you will get a 1-iodopropane as a major product, plus sodium chloride will be your side product. So your major organic product you are getting in this reaction is 1-iodopropane. Now for the second reaction of a tertiary halide with potassium hydroxides give alkene. Also, this includes the removal of beta hydrogen and also living group. Both are living. So this also known as dehydrohalogenation. That means hydrogen and halogen both are eliminating. OH negative here will act as a base. So if you see the reaction, we have this tertiary butyl bromide. This carbon which is attaching with bromine also attaching with 3 other carbons of methyl groups. So this is a tertiary butyl bromide. It is reacting with alcoholic potassium hydroxide and along with heat. So dehydrohalogenation happens and the beta hydrogen and leaving group, which is bromine, both will be removed. Beta hydrogen from one of the CH3 group, and you will get CH3C CH3 double bond CH2, that is 2-methyl propene as your major product, plus potassium bromide and water molecule will be your side product. Now if we see the third reaction of secondary bromide with the sodium hydroxide, this is a nucleophilic substitution reaction and the reaction will proceed via SN1 mechanism, substitution nucleophilic unimolecular. Here OH minus will act as a nucleophile. So what will happen? You have this 2-bromobutane. Okay, that means this bromine is attaching with this carbon, which is attaching with other 2 carbons. So this is a secondary alkyl bromide, 2-bromobutane. It is reacting with sodium hydroxide in presence of water and giving us an alcohol as a major product, that is butane 2-ol. So this bromine will be replaced by the hydroxyl ion, which is here acting as a nucleophile. Okay, this reaction is proceeding via SN1 mechanism. So in the SN1 mechanism, we follow 2 steps. The first step is the slowest step and rate determining step, which includes the formation of stable carbocation. So in the SN1 mechanism, stability of the carbocation is a key factor. So we got a major product in this reaction as alcohol, that is butane 2-ol after the replacement of bromine with the nucleophile, that is hydroxyl ion, plus sodium bromide will be your side product. Now if we see the fourth reaction, the reaction of a primary halide with potassium cyanide. Now this is an example of again a nucleophilic substitution reaction, and here the cyanide ion Cn negative will act as a nucleophile. Also this reaction will proceed via SN2 substitution nucleophilic biomolecular mechanism, which involves a single step reaction. So we have this bromoethane CH3CH2Br primary. Okay, so this is primary alkyl halide, so it will prefer SN2 mechanism, because for SN2 mechanism the primary alkyl halide which will going to give you a primary carbocation will be more reactive. Okay, or more reactive towards this SN2 mechanism. Okay, so primary alkyl halide will consider the SN2 mechanism for nucleophilic substitution reaction. So here this alkyl bromide reacting with potassium cyanide, and cyanide here is acting as a nucleophile, replacing the place of this bromine and attaching with this alkyl group, propyl group. So major product you are getting after the reaction of bromoethane and potassium cyanide in the presence of aqueous ethanol after nucleophilic substitution, you are getting major product as propane nitrile plus potassium bromide will be your side product. Okay, let's see the fifth reaction. this is a reaction with sodium phenoxide of alkyl halide. Okay, so sodium phenoxide with the alkyl halide result in the formation of ether. So you have this sodium phenoxide C6H5ONa when it reacts with chloroethane. So this is a Williamson synthesis. Okay, this reaction is a Williamson synthesis reaction, and what will happen? The sodium and the Cl will be eliminated, okay, from the reaction, and they will combine, and the remaining this sodium oxide and this chloroethyl, so ethyl group, and will going to join with the C6H5O, and you will get a ether as your major product. Here you are getting C6H5O C2H5. So this is an ether, your major organic product you are getting after the reaction of sodium phenoxide with this chloroethane plus sodium chloride will be your side product. Okay, this reaction is a Williamson synthesis reaction. Sixth reaction, if you see, we have again an alcohol. So alcohol when reacts with thionyl chloride, that is SOCl2, it will result in the formation of an alkyl halide. Okay, now SO2 and HCl gases, they are here in this reaction as a byproduct. Okay, so reaction with this of alcohol with the thionyl chloride, this is a preferred method. This reaction is a preferred method for the preparation of alkyl chloride. Why? Because the side products you are getting, that is SO2 and HCl, both are in the gaseous forms, so they will leave from the reaction mixture, leaving pure alkyl halide remaining in the reaction mixture. Okay, so you will get a pure alkyl chloride. 1-propanol reacting with thionyl chloride. So alcohol reacting with thionyl chloride giving us 1-chloropropane plus SO2 and HCl will be your byproduct. Both are gaseous form, so they will left from the reaction mixture, leaving behind pure alkyl chloride. So this is the preferred method for the preparation of this chloroalkyls. Next reaction is 7th, which is the reaction between alkene and hydrogen bromide. Also, this reaction is in the presence of peroxide. Okay, first of all, if you see that if you react a halogen acid, okay, or you can say hydrogen bromide, hydrogen halide with the alkene, then this reaction will be a addition reaction. Then you have to check whether this reaction is performing in presence of peroxide or in the absence of it. So we have 7th reaction in the presence of peroxide. So reaction will proceed via anti-Markovnikov addition rule. If there is no peroxide, which is present in the 8th reaction case, then it will proceed via Markovnikov addition rule, right? So your 7th reaction is performing or happening in the presence of peroxide between alkene and hydrogen bromide. So this reaction will proceed via anti-Markovnikov addition rule, which says that your negative part of the hydrogen bromide, where here it is bromide ion, right? So this negative part, that is bromide ion, will attack on that carbon on which, or you can say that double bonded carbon on which the hydrogen atom is more. So negative part is going to attach to the carbon having more number of hydrogen atom. So you have this but1-ene, that is alkene, CH3CH2 CH double bond CH2. When it reacts with hydrogen bromide in the presence of peroxide, it is going to follow the anti-Markovnikov addition rule, and this bromide is going to attach on that double bonded carbon having more number of hydrogen atoms. So in these two double bond carbons, this carbon having only one hydrogen and this carbon have two hydrogens. So the bromine will attach on this carbon and you will get 1-bromobutane as your major organic product in this reaction. Now let's see the last part or 8th part of this question. Reaction of an alkene with the hydrogen bromide. Now again this is an addition reaction, and reaction is proceeding in the absence of peroxide, so it will proceed via Markovnikov addition rule, which says that the negative part will attach to the carbon or to the double bond carbon which is having lesser number of hydrogen atoms. So we have this 2-methyl but2-ene as a reactant, CH3 CH double bond C, CH3 whole twice. When it is reacting with hydrogen bromide, it will follow Marconi addition rule, according to which this bromide is going to attack on this double bond carbon because it is containing no hydrogen, right? This double bond carbon containing one hydrogen and this containing no hydrogen. So this bromine will going to attach on this one carbon and you will get your major product as CH3, CH2C, Br, CH3, CH3. Okay, nothing happens, just double bond will be removed and one bromine will going to attach on this lesser number of hydrogen atom containing carbon, and this hydrogen from the hydrogen bromide will going to attach on this other double bonded carbon and you will get a alkyl bromide. Let's see our next question, the exercise question 6.18. Question is, para-dichlorobenzene has higher melting point than those of ortho and meta isomers. Discuss. So you have to tell that why para-dichlorobenzene has higher melting point comparatively to ortho and meta substituted isomers. So you have given some time, try to analyze this question, and then we will see its explanation. Okay, let's see. So for this question, we have to first of all compare between the para-dichlorobenzene, ortho-dichlorobenzene and meta-dichlorobenzene. So if you see the structures of these three isomers, this is ortho-dichlorobenzene because one chlorine is at para but another one is at ortho. Here, this is meta-dichlorobenzene because one chlorine is at the very first carbon at the para position but the another one is at meta position. Now this third one is para-dichlorobenzene because both the chlorine are on the para positions. So with respect to this one chlorine, the another chlorine is changing its position at ortho, meta and para, right? This is para positions, this one and this one. These two are ortho positions, they are equivalent, and these two are meta positions. They are also equivalent. Okay. So if you observe in these three compounds, only the positions are different of the chlorine, one of the chlorine atom, right? Still, your para-dichlorobenzene have higher melting point than ortho and meta isomers. So the para isomer, if you can see, it is more symmetrical. It has more symmetry. It will fit closely in the crystal lattice of the molecule. Para isomer has stronger intermolecular forces of attraction than the ortho and the meta isomers comparatively due to its symmetry. So during the melting, when you melt the molecule, so during melting in the crystal lattice, you have this para isomers. Okay. So during melting or dissolution, the crystal lattice will break and you will need a larger amount of energy to melt or to dissolve this para isomer then comparatively to corresponding ortho and meta isomers. Okay, so due to the symmetry of this para-dichlorobenzene, it will fit more symmetrically or more closely in the crystal lattice, due to why it has stronger intermolecular forces of attraction comparatively to other ortho and meta isomers. And when you do the melting or dissolution process, the crystal lattice of the molecule will break and you will need a larger amount of energy to melt this para-dichlorobenzene comparative to ortho and meta-dichlorobenzene, right? Now, this is why the melting point of para isomer is higher and also its solubility in the water or in the solution is lower due to its symmetrical structure than the corresponding ortho and the meta isomers. Okay, so para isomer is having more symmetry, due to which you will need larger amount of energy to melt or dissolve it, due to which the melting point of para isomer is higher. Also, its solubility is also lower corresponding or comparatively to the ortho and the meta isomers. Okay, let's see our next question. Exercise question 6.19. How the following conversions can be carried out? We have given some names of the product, something to something. Okay, so you have to tell how this conversion will going to be carried out. First is propene to propane 1-ol. We have selected some, some parts of this question because they are covering the major reactions. So first is propene to propane 1-ol. Then fifth, benzene to 4-bromo-nitrobenzene. 10th, 2-methyl 1-propene to 2-chloro 2-methyl propane. 12th is but1-ene to N-butyl iodide. 17th is chloroethane to butane. 18th, benzene to biophenyl. 19th, tertiary butyl bromide to isobutyl bromide. And 16, 2-bromopropane to 1-bromopropane. So you have given some time, try to analyze this question, and then we will see the correct process for each of the parts. Okay, let's see. So let's see for the first part, propene to propane 1-ol. Propene can be converted to an alcohol, propane 1-ol, through the anti-Markovnikov addition rule, which was followed by nucleophilic substitution reaction. So you have to follow two steps. First is anti-Markovnikov addition. After the addition of propane into some halogen acid, okay, or hydrogen halide, and then it will be followed by nucleophilic substitution reaction. This is your, you can say, propene. Now it is reacting with hydrogen bromide, okay, hydrogen halide, in the presence of peroxide. So it will follow anti-Markovnikov addition, okay, and you will get your product as CH3, CH2, CH2Br, because this negative part will going to attack on the carbon containing more hydrogen, which is this. So CH3, CH2, CH2Br. So this one, this one position specifically, you are performing anti-Markovnikov addition, okay. So CH3, CH2, CH2, bromine will attack on this one carbon. Now you have to do simply the nucleophilic substitution reaction with the aqueous KOH and heat, and you will get your major product as propane 1-ol, that is CH3, CH2, CH2OH. So bromine will be replaced by hydroxyl nucleophile. Okay, so for this one position, you are performing this anti-Markovnikov addition of propene and getting 1-bromopropane, from which after the nucleophilic substitution reaction with hydroxyl ion as a nucleophile, you will get propane 1-ol as your product. So this is the whole conversion from propene to propane 1-ol. Now let's see for the fifth reaction, or you can say fifth conversion, benzene to 4-bromo-nitrobenzene. Now this reaction of benzene with the bromine results in the formation of bromobenzene, which was further followed by nitration, and it will yield 4-bromo-nitrobenzene. So this is your benzene. You do the halogenation of this with the bromine molecule in presence of FeBr3 in the dark condition. Dark condition is very important because you are taking benzene, so you have to use the dark conditions. If you are using any alkanes, okay, alkyl groups, then you have to provide a UV light condition, okay, for the activation of alkyl group and for the free radical mechanism, okay. But here in the benzene ring, you have to perform this reaction in the dark condition. After the halogenation with the bromine molecule, this benzene will convert into bromobenzene. Now this bromobenzene, you have to do the nitration process in presence of HNO3 and sulfuric acid. You will get 4-bromo-nitrobenzene, nitro group substituted, or you can say nitro-substituted bromobenzene. Okay, so this is the conversion of benzene to 4-bromo-nitrobenzene. For the 10th part, 2-methyl-1-propene to 2-chloro-2-methylpropane. You have to follow the Markovnikov addition rule of 2-methyl-1-propene. It will yield 2-chloro-2-methylpropane. So you have to take 2-methyl-1-propene, then you have to react it with hydrogen chloride, HCl, following Markovnikov addition, which says the negative part will attack on double bonded carbon containing lesser hydrogen. That means this one carbon. So you will get 2-chloro-2-methylpropane as your major product. So this is the conversion of 2-methyl-1-propene to 2-chloro-2-methylpropane. And as I said, for the specific position of this chlorine in the final product, you have to perform the Markovnikov addition of this alkene. Now for the 12th part, but1-ene to N-butyl iodide. So addition of bromine to alkene, which is but1-ene here, via anti-Markovnikov addition yields 1-bromobutane, which was converted to N-butyl iodide through halogen exchange method or Finkelstein reaction. So if you have this but1-ene, CH3, CH2, CH double bond CH2, you react it with hydrogen bromide in presence of peroxide because you are following anti-Markovnikov addition. So this bromide will react on this first carbon, which is containing more hydrogen, and you will get 1-bromobutane from this reaction. Then you have to perform the Finkelstein reaction or halogen exchange method after the reaction of this 1-bromobutane with sodium iodide in the presence of dry acetone, and you will get N-butyl iodide as your major product. So this is the conversion of but1-ene to N-butyl iodide. Now for the 17th process, that is chloroethane to butane. Through the Woods reaction, the chloroethane can be converted to the butane molecule. So chloroethane you have to react it with the sodium metal in presence of dry ether. What will happen? You will get a product containing double the number of carbon atom comparative to reactant. So your reactant have 2 carbon atoms, your product has 4 carbon atoms. Butane. CH3, CH2, CH2, CH3 plus 2 NaCl will be your side product. This is Woods reaction when you get the final product containing double the number of carbon atom of compared to reactant. Okay, so through Woods reaction you can convert the chloroethane to butane. Now let's see the 18th conversion, that is benzene to biophenyl. So bromination of benzene will yield the bromobenzene, which will yield the biophenyl through performing Fittig reaction. So when you take the benzene, you react it with bromine molecule for the bromination. In the presence of FeBr3 and dark condition, you will get a bromine substituted benzene ring, that is bromobenzene. And then you have to perform the Fittig reaction in the presence of 2 sodium metal and dry ether. So this is Fittig reaction. What will happen? The 2 benzene rings will attach together and gives us the product as biophenyl or diaphenyl plus 2 sodium bromide will be your side product. So this is the conversion process for benzene to biophenyl. Now for the 19th part, tertiary butyl bromide to isobutyl bromide. Dehydrohalogenation you have to do. Then you have to perform the anti-Markovnikov addition, which will yield isobutyl bromide from the tertiary butyl bromide. So you have to take this tertiary butyl bromide, okay. Then you have to react it with alcoholic KOH in the presence of alcoholic KOH. Then dehydrohalogenation happens. So halogen along with hydrogen will be removed, beta hydrogen, and you will get an alkene, 2-methylpropene. Then you have to react it with hydrogen halide, that is hydrogen bromide, in presence of peroxide, and it will follow anti-Markovnikov rule. So bromine will going to attack on this carbon containing more hydrogen, and you will get a isobutyl bromide as your major product. This is the conversion for tertiary butyl bromide to isobutyl bromide. the 16th part, 2 bromopropane to 1 bromopropane. So for this, the dehydrohalogenation will you have to do. Then you have to follow it by anti-Marconic addition, which will yield 1 bromopropane from 2 bromopropane. So you have to take 2 bromopropane and then you have to react it with alcoholic potassium hydroxide. The dehydrohalogenation will happen. The bromine along with beta hydrogen will be removed and you will get an alkene, that is propene, right? Plus hydrogen bromide will be your side product, and then you have to perform the anti-Marconic addition with hydrogen bromide in presence of peroxide. The bromine will going to attack on this carbon containing more hydrogen and you will get the means product as 1 bromopropane. Okay, so this is the conversion of 2 bromopropane to 1 bromopropane. Okay. Okay, thank you so much. That's all for today's chemistry session. Thank you.